We are standing somewhere inside a story that is 13.8 billion years long, a slow unfolding of galaxies and light that stretches so far behind us we cannot see its beginning. But if we trace that line backward, past every star and every silent epoch, we hit a single, impossible wall. What was there before that? The question feels natural, almost childlike, yet the moment you ask it, the universe pushes back with a deeper contradiction. Because if time itself did not exist yet, then what does before even mean? The answer, when it finally lands, will not just surprise you, it will shatter the very intuition you are using to ask the question right now. Tran Minh, a 28-year-old physics teacher in Ho Chi Minh City, was caught off guard one evening in 2023 when a student asked him, "Teacher, what came before the universe?" He stumbled through a vague answer, and the silence that followed was heavy with his own uncertainty. Over the next 3 months, he buried himself in over 40 scientific papers and 2 books, determined to find a better response for his 11th grade class. When he finally had an answer, it wasn't the neat, explosive story we all picture. His reply was that the question itself was flawed. The fundamental misunderstanding is that the Big Bang was a bomb going off in the middle of empty space. But that image is completely wrong. According to NASA's Wilkinson Microwave Anisotropy Probe data from 2012, the event did not occur at a single point in space. Instead, space itself expanded, making the question, where did it happen, a linguistic mistake. And the initial singularity, as Roger Penrose explains in Cycles of Terms of Place at All, it was a boundary of space-time where the laws of modern physics break down, like an event horizon of a black hole, but existing inside everything. So, before you can even ask about a before, you have to realize that the very concept of a location for the beginning is meaningless. Time itself might not have existed, a notion supported by Einstein's general relativity, where time is just another dimension of space-time, making before physically nonsensical. Here is the first step to resetting your intuition. Think of a singularity in mathematics, like dividing by 0. It doesn't give you a place, it gives you an undefined answer. So if there is no central point where the explosion happened, where is this before you're looking for? Imagine the early universe not as a dark, empty void, but as an intensely hot, opaque plasma, so dense that light itself couldn't travel freely through it. This was the state of everything for the first 380,000 years. To truly abandon the image of an explosion, consider the idea proposed by physicist Alan Guth in 1980, known as cosmic inflation, which suggests the universe underwent a period of hyperfast expansion in the first fraction of a second. This rapid stretching of space itself, rather than a blast of matter into a pre-existing void, smooths out the universe to the remarkable uniformity we observe in the cosmic microwave background. The incredible scale of this initial burst is hard to grasp, but we can measure its afterglow. The temperature of this infant universe just 1 second after its birth was a staggering 10 billion Kelvin. That is unimaginable heat, enough to shatter the nuclei of atoms themselves. Now, as this primordial soup expanded and cooled, it crossed a critical threshold at 380,000 years, dropping to about 3000 Kelvin, the exact temperature at which electrons and protons could finally bind together. This moment of recombination allowed the universe to become transparent for the first time, and the light released then is the oldest thing we can possibly observe. The crucial takeaway is that this cosmic microwave background isn't a photograph of the moment of creation. It's a snapshot of a much later, cooler universe, a wall that represents the absolute limit of our vision. So, when we look back and ask what came before that glowing wall of plasma, we're not just looking at a puzzle of space, but of time itself. The entire history of everything we can ever see is contained in the expansion that followed this singular moment. The very space that we occupy, the space between the stars in your own backyard, is the same canvas that has been stretching since that unimaginably hot beginning. To understand the universe is to understand that its story isn't about an explosion in space, but the expansion of space, which is a profound distinction. You might think the question of what came before the Big Bang is a modern one, born from our latest telescopes and particle accelerators. But the philosopher Thomas Aquinas posed it in 1270, asking what God was doing before creating the heavens and the earth. A puzzle that has now haunted us for over 750 years. The instinct to picture an empty, dark void ticking away in anticipation is powerful, yet it collapses when we consider Augustine of Hippo's argument from 400 AD. He reasoned that time is not a stage where events unfold, but a property of the created world itself, meaning God didn't create something in time, he created time. So saying there was a blank period before the Big Bang is a logical misstep, because at the very moment of T0, neither space nor time existed to contain any event at all. The laws of physics, as Lawrence Krauss puts out, suggest the universe itself may not need a cause, because causality is a concept that only makes sense after time begins. I remember a content creator in Hanoi, a 35-year-old woman named Ha, who after watching a video on the multiverse confessed that she stopped fearing failure, realizing her mistakes were just a draft in one of countless realities. To truly grasp this, try thinking of time not as a container, but as a relationship between events, a concept championed by Augustine and later Kant, meaning there is no such thing as an empty moment. So if nothingness isn't a void, what exactly birthed our universe? In 1970, Stephen Hawking and Roger Penrose proved that if general relativity holds true, the universe must have begun as a singularity, a point of infinite density where the laws of physics break down. But this isn't a place in space, it's a boundary of space and time itself. In quantum cosmology, researchers use the Hartle-Hawking wave function of the universe to describe the universe appearing like a quantum particle from quantum nothing. This leads to the remarkable no-boundary proposal. The universe may be infinite in space but finite in time, just like the surface of the Earth. You can travel around it forever without ever hitting an edge or a starting line. Consider what that means for our question. If you walk north on Earth, you'll never find the first point of the planet. The surface simply curves back on itself. The no-boundary model suggests time behaves the same way, so asking what came before is as meaningless as asking what lies north of the North Pole. This idea was profoundly illustrated in 2004, when Hawking conceded a famous bet to John Preskill about black holes and information loss, paying up with a cricket encyclopedia. In his announcement, he declared that information isn't lost, but it doesn't return simply either, which forces us to completely rethink space-time before the Big Bang. To grasp his solution, you have to meet imaginary time, a concept where time is treated like another dimension of space, blurring the distinction between a beginning and an endless loop. Instead of a moment where everything snaps into existence, the universe could be a self-contained sphere of space-time with no singular point of creation. So, if time doesn't have an empty starting point, then what does the idea of nothing even mean? We tend to picture nothing as an empty box, a silent, dark void with zero content. But in quantum physics, that assumption shatters completely, because what we call the vacuum is actually a seething storm of energy. The vacuum is not a place of emptiness, it is a place of furious, invisible activity, with an energy density that defies all logic. Here is the uncomfortable truth. According to a 2013 report in Scientific American, a single cubic centimeter of empty space contains an energy density of up to 10^113 joules, a number so absurd it could be the very source of our universe. Think about that for a second. How can a dark, silent void hide that much raw power? It is as if the very fabric of reality is vibrating with potential, completely changing what we mean when we say nothing. To make this even more bizarre, the American Institute of Physics noted in 2015 that while the observable universe holds roughly 1080 real particles, the number of virtual particles popping in and out of existence in any single cubic centimeter could actually surpass that total. So the nothing between your fingers is busier than the entire cosmos filled with stars, making our everyday concept of a void look utterly naive. This might sound like pure theory, but history proves the universe loves these surprises. As two engineers at Bell Labs famously discovered in 1965, Arno Penzias and Robert Wilson were frustrated by a persistent hiss in their antenna that they could not eliminate, even after cleaning out the pigeon droppings they suspected were causing it. When the noise stubbornly remained, they realized they were hearing the echo of the Big Bang itself, a relic from 13.8 billion years ago that they had stumbled upon by pure accident. Penzias later recalled at his 1978 Nobel ceremony that their discovery was, in his own words, a lucky mistake, proving that the deepest secrets often hide where we least expect them: the vacuum, empty space, nothing at all. Yet quantum field theory predicts that this nothingness seethes with energy, humming with a density so absurd it practically breaks the calculator. This is the cosmological constant problem, what some physicists call the biggest embarrassment in all of theoretical physics. A discrepancy so vast it suggests our understanding of the universe is fundamentally incomplete. So, let's translate the raw numbers into something we can grasp, because the scale of this failure is breathtaking. The quantum field theories we use to describe the subatomic world aren't just a little bit wrong about the vacuum. They're wrong by a factor of roughly 10 to the 60, or even 10 to the 120, making it the worst prediction in the history of science. If the vacuum energy were as large as our most successful theories propose, the universe would have blown itself apart in a fraction of a second, yet here we are, observing a cosmos that is stable, structured, and billions of years old. This chasm between what we calculate and what we observe is the mystery of dark energy, a force that makes up about 68.3% of the universe's total energy budget, according to the Planck mission results from 2018. The matter we are made of, every star, planet, and galaxy we can see, accounts for a paltry 4.9%, while dark matter and invisible scaffolding holds another 26.8%. We are floating in an ocean of unknowns, and the only thing we know for sure is that the map we have is missing almost every major landmark. So the next time you hear a confident claim about the origins of everything, try a simple experiment. Pick one, write it down, and then look for the counter-evidence. The very fact that our theories are so broken doesn't mean we've failed. It means we're standing at a frontier, and the confusion you feel right now is the same confusion that drives science forward. Roger Penrose spent decades convinced that the standard story was incomplete. In 2023, he pointed to odd circular patterns in the cosmic microwave background, which he called Hawking's points, and claimed these were scars left by a universe that existed before our own. Colleagues at Princeton pushed back, questioning the signals and the statistics, yet Penrose never wavered, igniting a fierce debate about a cyclical cosmos. So here is the uncomfortable truth. Science has no single, locked-in answer, and the idea of a single beginning has competitors that are taken very seriously. Another possibility is the Big Bounce, proposed by Carlo Rovelli and the Loop Quantum Gravity School, where the universe didn't start from a singularity but collapsed to a maximum density and then rebounded outward. Then there is the cyclic model from Paul Steinhardt at Princeton, which imagines two parallel membranes colliding every 10 billion years to birth a new Big Bang with no absolute starting point at all. Andre Linde at Stanford went further, suggesting our universe is merely one bubble in an infinite multiverse that has been growing since 1983, making the question of before meaningless because there is no single origin. Penrose's own conformal cyclic cosmology says we are in the 13th eon, and that each eon stretches for roughly 10 to the power of 100 years, with our Big Bang being just the handoff from the 12th. You might feel the ground shifting under you, but this is precisely where real science lives. Why does that matter to you? Because if experts can't agree on whether there was a bounce, a collision, or a multiverse, then the phrase "science has the final answer" becomes the most unscientific statement you can make. So as a first step, confront the three common misunderstandings head-on. The Big Bang was not an explosion happening inside a region of space. There was no infinite night before it, and modern physics does not claim to explain everything. These four models alone prove the field is still searching, which raises the next pressing question. If observation has such limits, how can we ever really see what came before? So we have all these competing models, each offering a different answer to what happened before everything we see. Yet here is the catch. No matter how elegant the mathematics, the universe keeps a hard boundary that we simply cannot see past. The Planck satellite data from 2018 gives us the age of the universe as 13.8 billion years with remarkable precision. But that measurement itself only reaches back to a moment 380,000 years after the beginning. Everything earlier than that is completely opaque to our instruments, a fog that no telescope has yet penetrated. Light and any other form of information from before that era is blocked by what we call the wall of fire at recombination, meaning the early universe is forever hidden from direct observation. Even the James Webb Space Telescope, operating since 2022 and capturing galaxies from 13.5 billion years ago, hits the same cosmic barrier when trying to look further back. Why should we trust any narrative about the first fraction of a second if we cannot observe it? On March 17, 2014, the BSEP-2 team at the South Pole announced they had detected gravitational waves from the inflationary period, direct evidence of what happened before the Big Bang. The world of physics erupted with excitement, because this would have been the smoking gun for a whole class of theories about the earliest moment. Then came the fall. After months of scrutiny, the team had to admit their signal was simply galactic dust, not primordial gravitational waves at all. That moment became a powerful lesson in how easily we mistake our desires for evidence, and how the observable boundary humbles even the most confident claims. If we cannot confirm what happened in that first tiny slice of time, then every model we discussed remains a beautiful guess rather than a proven answer. Here is what you can do in the next 15 seconds. Imagine the temperature dropping from 1032 Kelvin down to the 2.7 Kelvin we measure today, and notice that vast gap where our knowledge goes dark. The data simply stops at that wall, and beyond it, there is only silence from the universe itself. So when we ask what came before, we are asking a question that our instruments may never be able to answer directly. Maybe the truth is that we have to live with this limit, understanding that some doors are closed to us forever. But if we cannot look back further, does the question itself lose its meaning, or does it simply become a matter of philosophy rather than physics? There is a quiet humility that comes when the numbers do not add up, yet they are the best we have. Adam Riss and his team pointed the Hubble Space Telescope at distant supernovae and calculated that the universe is expanding at roughly 73 kilometers per second per megaparsec, a figure published in the Astrophysical Journal in 2019. But then you look at the cosmic microwave background, the faint echo mapped by the Planck satellite, and it tells you a different story, one where the expansion rate is closer to 67.4. The gap between those two measurements is what physicists call the Hubble tension, a persistent, unsolved crack in our understanding of the cosmos, a crack that should make us all pause and wonder if our map of reality has a fundamental flaw. Consider how strange it is that the standard model of cosmology, called LUCDM, only needs 6 free parameters to match the entire observable universe, a fact so improbably simple that the Planck collaboration itself flagged it as suspicious. A system containing over 10 trillion galaxies, from colliding black holes to boiling nebulae, can be described by just half a dozen dials we can turn. And then there is the flatness problem, where the Planck data shows that space is flat to a precision of 99.9%, meaning the total energy density is almost exactly 1. A condition so delicate that any meaningful deviation would have either collapsed the universe long ago or torn it apart before stars could form. So we are left with a cosmos that looks too perfect, a universe that fits our equations a little too neatly, and that is not a triumph. It is a warning that we might be missing something vast. When I think about James Peebles accepting his Nobel Prize in 2019, I remember how he did not celebrate certainty but instead urged young scientists, do not rush to accept everything. Learn to live with ignorance and keep observing, because roughly 68% of the universe is dark energy and another 27% is dark matter, both utterly invisible to us, both completely unexplained by any experiment we have ever run. So, what is the practical step we can take from all this? If you are following along with the earlier steps, the final move is to accept that there is no single absolute answer. Instead, you hold at least 5 competing scientific hypotheses in your mind at once, each of them incomplete, each of them promising, and you let that discomfort teach you more than any false certainty ever could. That is the lesson of modern cosmology. The more precise our measurements become, the more mysterious the whole picture grows, and the deeper we stare into the sky, the clearer it becomes that our ignorance is not an obstacle, but the very engine of all future discovery. We began with the question, what was there before? And the deepest answer science can offer is that the question itself may be broken. Before is a word we invented inside a universe that had a beginning. We pictured nothing as an empty room, but the void is a seething storm of quantum energy, a place where the laws of physics themselves lose their meaning at the singularity. We learned from a 2020 survey by Physics Today that, while about 70% of cosmologists are confident the Big Bang happened, fewer than half believe we can ever know what preceded it, a beautiful admission of our limits. This uncertainty isn't a failure, it is the engine of discovery. Look at the Hartle-Hawking model, which sketches a universe with a wave function of unimaginable complexity, where our own cosmic existence is but one probability among 1077 possibilities, a number so vast it makes the mind spin. We are a staggeringly unlikely outcome, a whisper of order in a chaotic sea of potential, a Boltzmann brain dream that somehow became a waking reality. So when we search for the origin of everything, we are really searching for a definition of ourselves. Creatures born from a void that was never truly empty. And perhaps that is the most humbling and magnificent truth of all. We may never find the final answer, but the search itself is the very reason we are here, and that is enough.